All right. Good afternoon, everyone. How are you all? All right, so our goal today is to finish up chapter 15 material. We only have maybe one and a half sections left. Friday, we're going to start chapter 16. You have an exam on Thursday next week. So the exam is going to cover where we left off in chapter 14, all of 15, and then through 16 sections 1 through 4 is going to be on the exam. Okay. And that's all in the syllabus, so you can take a look at what that is there. But that's Thursday next week in recitation. Questions before we get started? Yeah.
So practice materials for exam 1. When are practice tests for exam 2?
The question is, when are practice exams going to be posted for midterm 2? I'm not sure, but I assume it will be hopefully by the end of the week, if not early in the week. But yeah, I don't get updates on that, unfortunately, and I don't do the posting of them. So, yeah. Other things. Okay. All right. Last time we were talking about predicting the direction of a reaction. And we used the reaction quotient Q to be able to predict the direction. So if we kind of go over a few things here, we already looked at calculating K, the equilibrium constant. We looked at what the value of K means. Okay? If K is greater than 1, we have favors the products. The reaction favors the products. There's more products at equilibrium than reactants. If K is less than 1, this favors the reverse reaction, or it's reactant favored, more reactants at equilibrium. If we want to figure out concentrations of various substances at equilibrium, we'll use our ICE tables. So we use concentration in these tables. Look at the change during the reaction based on the stoichiometry, that kind of thing. So then, what we then started with last time is looking at reaction quotient. So let's say you're given a set of concentrations for all of the reactants and products in a chemical equation, and you want to figure out if those concentrations represent equilibrium. We'll use the reaction quotient Q to determine if they are at equilibrium. If we find that we are not at equilibrium, which way will the reaction proceed to reach equilibrium? Will we form more reactants, or will we form more products? Okay. So we looked at reaction quotient, like I said. If Q is less than K when we calculate these, essentially what that means is that the product concentration is less than the reactant concentration, then there should be at equilibrium, okay? So compared to at equilibrium, which means that the reaction is going to proceed towards the products. So we need to produce more products to get to equilibrium. And the opposite is true if Q is larger than K. There's essentially more products than expected to be at equilibrium, and so we need to produce more reactants. The reaction occurs in the reverse direction. Questions on any of these things? All right. Q is less than K. Reaction proceeds towards the products. Or did I get that wrong on that slide? Q is greater than K. That's right. Q was 36. Okay, so reactant proceeds towards the. We also looked at this problem. We were trying to determine if the reaction was at equilibrium. I just posted this morning. So if you need to go and look at those, they are on Carmen now. I want to look at this problem. We've sort of been looking at this one throughout the chapter. And we have in this box a a red molecule that represents A2, and then a blue molecule that represents B2, and then 2 AB is formed. So that's one blue sphere attached to one red sphere. If we assume that each molecule in this box represents 1 mole per liter, we can determine if this reaction mixture is at equilibrium, basically by counting up the number of A2, the number of B2, and the number of AB. Okay? So if we do that, we have 1 A2 present in this container. So that's 1 mole per liter. Oops. For B2, we have 1 of those. Where am I at here? And for AB, let's see, we've got 1, 2, 3, 4, 5, 6. And so, just using these very generic, this generic reaction with this figure, we can calculate Q. Q is going to be equal to the concentration of AB squared. So the squared comes from the stoichiometric coefficient, divided by A2 times B2. Those are their concentrations. Okay? So plugging in these values that we've determined based on simply counting these molecules that represent 1 molar each, we're going to get 6 squared in the numerator and 1 times 1 in the denominator, which gives us 36. So this is our value for Q. In the problem, we're given that K is 1.5. Therefore, Q is greater than K. And so which way is the reaction going to proceed? Towards the reactants or the products? Yeah, it's going to go towards the products to reach equilibrium. Okay, so everyone see how we're going to do that? All right. What's that? Yes. Okay, sorry. Yes. Erase that, everyone. Q is greater than K, so the reaction proceeds towards the reactants. We'll erase that, maybe. Okay, thank you. All right. Okay, so what we're going to do now is apply this Q versus K concept to changes that we make on a reactor. And what this is referring to is Le Chatelier's principle. So this is basically like if we change a concentration of a reactant or a product, what happens to the equilibrium? Which way does the reaction shift? If we change the volume, if we're dealing with gaseous substances, what happens? If we change the temperature, what happens? Okay. So we are going to take a look at this ammonia reaction again. But before we get to that, I want to do something a little bit simpler. Okay. I'm going to add another. Okay. So we're looking at our ammonia formation. So this is just a very general slide. We're not going to do any math necessarily here. So we're going to say what happens if we increase the ammonia concentration. Okay, so we're increasing the concentration of product. That's going to make our Q larger than K, and so we're going to form more reactants. Okay. which means we form more N2 and more H2 in their stoichiometric proportions. If we increase one of the reactants, Q is going to be less than K, we're going to form more products. Okay? Whiteboard here. So let's say we have a very simple equilibrium of A in equilibrium with B, right? And this was going to have an equilibrium constant of 11.5. So we could go through, and let's assuming we have, how do I do that? Let's see, assuming we have a starting concentration of 1 mole per liter for A, we could get our equilibrium concentrations for A and B. I'm not going to work through that because that's not really the important part of this. But let's just say that at equilibrium, we have a concentration of A of 0.08 moles per liter and a concentration of B of 0.92 moles per liter. So we notice we have a large value of K, it's greater than 1. This tells us that the reaction is going to be product favored. And you can see based on the concentrations, we have a larger concentration of product. Okay? So that all is holding true. So what happens if the concentration of A is increased to 0.5 molar from its equilibrium concentration of 0.08? So we've got the reaction at equilibrium, and now we add more A so that the new concentration is 0.5 moles per liter. Okay? We need to figure out which direction will the reaction proceed. And so we can do that by solving for Q. Which direction does the reaction RxN proceed? Okay. So in solving for Q, we're going to have Q equals the concentration of B over the concentration of A. We know we're not at equilibrium, okay? So we're not exactly using our equilibrium concentrations. We're using our new concentration of A, which is 0.5 molar. And we didn't change the concentration of B, okay? So that's 0.92 molar. Now all that I'm showing you is that we're just playing with ratios. Okay? We had a ratio at equilibrium of 0.92 over 0.08. Okay? Now we're increasing the value in the denominator. All right, so we're changing our fraction. And so when we calculate Q, we're going to end up with a value of 1.84. And so when we compare Q to K, we're going to find that Q is less than K. And so what's going to happen to the reaction? Which way does it go to reach equilibrium? It's going to go towards the products. Okay. So I'm bringing us back to a really simple example here where we just have one product over one reactant. Because I just want to show you how we play with the numbers. Right? If we were to, at equilibrium, remove some of that product, remove some B. Now we decrease the value in the numerator of that fraction. Okay? And then we're going to end up with a Q that's larger than K. And so in that case, we need to form more products. And so what we end up finding out is that this is there's the principle that we're going to use is Le Chatelier's principle, in that whenever we add reactants to a mixture at equilibrium, it's going to force the reaction to form more products. If we're able to remove some product from a reaction at equilibrium, that's also going to form more products. Okay? If we add more product at equilibrium, we're going to shift back to the reactants, form more reactants, and so on. Okay? Mathematically, you can take this really simple example and prove that to yourself if you need to. Okay? Questions on this, and we're going to go back to our previous slide. Yeah. Yeah, so the question is K a constant that's dependent on the mechanism of the reaction? Yeah, K is a constant at a given temperature, so it can change at different temperatures, and we're going to see that especially next chapter. And it's essentially dependent on the rates. If you remember from the very early on in this chapter 15, we said that the equilibrium constant K is equal to the rate in the forward direction over the rate of the reverse. So that and those are dependent on the mechanism. So yes, that is exactly right. Other questions? Okay. So let's. So there's a number of other ways of shifting towards reactants and products by changing concentration. Again, just playing with whether we increase or decrease concentrations of reactants or products. Okay, and you can kind of think about this as like a seesaw. We have our reactants and our products, and we take away some products. In order to make that equal again, we have to add more weight to the product side. Okay, we need to form more products. I think there's a demo that I need to grab that they just got finished in the demo lab space that sort of is like a seesaw example. So I might try that on Friday. Okay, so first thing with Le Chatelier's principle, you add or remove reactant or product, you shift the equilibrium. Okay, so make sure you're able to predict which way you can shift the equilibrium. Questions on that? And if you ever don't know, you can plug in some numbers and make it work into K and Q. Here's a graphical example of adding hydrogen to our ammonia formation reaction. So in this graph, we have partial pressure of the gases on our y-axis and time on the x-axis. Okay? And we have reached equilibrium. We have different concentrations of hydrogen, ammonia, and nitrogen in their stoichiometric proportions. At least they should be. And then we're going to add some hydrogen. So you can see there's a sharp increase in the concentration of hydrogen. The only way to get such a sharp increase would be to actually physically add hydrogen in that case. And then what we see is that the concentration slowly decreases until it flattens out again, where we reach equilibrium. The concentration, of course, is decreasing because the hydrogen is reacting with the nitrogen to form ammonia. If we look at what happens with the ammonia concentration, it slowly increases until we reach equilibrium, and the nitrogen concentration slowly decreases until we regain equilibrium there. Okay? Make sense? We can remove some ammonia somehow from our reaction. We'll just isolate ammonia and remove it from the reaction flask. And you can see what happens to the concentrations of other species after we remove that ammonia. So we remove the ammonia. We need to form more product in order to regain equilibrium. Hydrogen's going to decrease, nitrogen's going to decrease. Okay. All right. Questions on changing equilibria by adding or removing reactants or products, changing concentration. Now we are going to look at how to affect our equilibrium by changing pressure. So there's 3 ways we can change pressure in a system. We can add or remove gaseous product or reactant. We can add an inert gas, inert meaning it doesn't react. And the last one is that we can change the volume of the container. And if we think about what that means, we're going back to PV equals nRT. If we change the volume, if we decrease the volume, the pressure is going to increase. If we increase the volume, the pressure decreases. All right. So I apologize for anyone who is red-green colorblind. We're going to make some notes here. We've got a general reaction of A forming B, 2A forming B. And in this box, there are 10 A spheres and there are 7 B spheres. Okay. So we're going to first look at what happens if we decrease the volume of the box. All right. So now we are basically squeezing those molecules closer together. All right. And we're disturbing the equilibrium. All right. So what do you expect is going to happen? Are we going to form more products or more reactants? Getting more products formed? Okay. So I didn't tell you the key here on how to figure this out. But essentially what happens is that when we increase the pressure, the side with the fewer moles of gas is favored. Okay, so side with fewer moles of gas is favored. So if we have an equilibrium where we have gas and then some other stuff, right, we really only care about the gas if we're changing the volume. Okay. And from our equilibrium, we have 2 moles of A that are reacting to form 1 mole of B. And that's just from the stoichiometry. So when you're thinking about which side, reactant or products, has more moles of gas, just add up the stoichiometric coefficient. Okay. So when we decrease the volume of this box, we increase the pressure. The side with fewer moles of gas is favored, and that ends up being the product side. So we should form more products. And I could circle that. We can show what we have in terms of our graphic here. We have 2 A spheres and 11 B spheres. So we've gone from 10 of A down to 2, and then up from 7 of B to 11. Okay. I don't know if that mathematically makes sense, but we'll just play it along. Okay, so then the other option is what happens if we increase the volume. decrease the pressure, is actually going to favor the side with more moles of gas. And so we should expect that more reactants are formed in this case. So it's just the opposite. Okay? If we increase the volume, decrease the pressure, side with more moles of gas is favored. Yes.
Is that just because A has two unknowns?
Yes.
So if they were both one, it would be.
Yes. So I was just going to go there. Thank you again for getting to my segue. So I was going to ask, what happens if we have 1 mole of A in equilibrium and 1 mole of B, and we change the pressure? Which side is favored?
Neither?
Neither. Yes. No change to the equilibrium will occur. Okay. There's no major change in the moles, right? There's no change in the moles on reactants and products, and so nothing happens to the equilibrium. And then here's our count. In this box here, we have 16 of A and 4 of B. Yeah, that's a dumb figure. We had initially 17 spheres, then we had 13 spheres, now 20. Change that one out next year. Okay, anyway, summarizing what we know about changing pressure. So 3 ways to change the pressure. Adding or removing gaseous product or reactant. Okay? So if we have a container that has only gases in it, we are able to remove one of them. This is kind of the ammonia example. This is exactly the same as affecting the concentration. So removing a reactant or a product. We remove a product, more product is formed. If we remove reactant, more reactant is formed. If we add reactant, what's formed? Product is formed. And if we add product, reactant is formed. Those are our 4 basic options. All right. And I think in the homework, they like to ask you what happens if we add a gas that isn't in the equilibrium. Okay, it's an inert gas. It does not react. This does increase the pressure in the container. There's now more molecules pushing along on the sides of the container. But this does not affect concentration or partial pressures of the gas in the equilibrium. So if it's an inert gas, it does not react, it does not affect the equilibrium. And then that third one we just looked at, changing the volume. Yes, Garrett, sorry. Yeah.
Well, with adding the gas, it would increase, it would increase the pressure, so why doesn't it change?
It increases the pressure on the container, but it is, because everything's in the gas phase, it's unlikely to force those molecules closer together enough that it causes a change in equilibrium. If those are along the lines of your thinking. Yeah, because I can imagine, sitting here thinking, okay, I've added an inert gas, that means everything has to get tighter together. But because we're still in the gas phase, those molecules are still relatively far apart.
When we were doing like the examples with the images, are we referencing the say the amount of of A in the picture, or are we just referencing the equation with the 2 in front of A, like the coefficients?
Yeah, just the equation. So really the spheres meant nothing. They're just to try try to show you that more product just will increase the volume of the container, whichever it was. Yeah, so when we're looking at changing the volume of the container, this last example here, we're only looking at the stoichiometry for that reaction, just in the equilibrium equation. So if we, over here, if we reduce the volume of the container, so we increase the pressure, the reaction is going to respond by reducing its volume. Okay, that's the other way of thinking about that. Okay, which means, and it does that by decreasing the number of gaseous molecules. So the equilibrium shifts to this side with fewer moles of gas. That's just a restatement of what we just did. And then the opposite is true. If we increase the volume of the container, equilibrium shifts to the side with more moles of gas. Questions? Yes.
What if the reactant is not enough to form more or not? What if you increase the pressure?
So the question is, if we are talking about a reactant that is a limiting reactant, what happens if we increase the pressure? So assuming we can still, well, this is still going to follow the same rules, but because it's a limiting, it can only go so far. So you eventually might run out of, if it's a reactant, it might run out of that reactant. Yeah. Other questions? Okay. All right, so another way to affect the equilibrium is to change the temperature. And if we're to determine how the reaction will proceed to regain equilibrium after changing the temperature, you need to know one critical piece of information, and that is whether the reaction is exothermic or endothermic. Okay? So we must know exothermic or endothermic for the reaction. And I wrote in the next bullet point here, temperature equals heat. Okay? As a reminder, we are going to be thinking about adding heat or removing heat from the reaction. So increasing the temperature or decreasing the temperature. The way that I think is easiest to approach this type of problem, or thinking about how the temperature affects the system, is to think about whether heat is a reactant or a product. Now, if we have an exothermic reaction, that when that reaction proceeds, it feels hot, it gives off heat, which means that heat is a product. Okay? For an endothermic reaction, something that feels cool, heat is absorbed, but essentially what we come down to is that heat becomes a reactant. Okay? So if it's exothermic, heat is a product. If it's endothermic, heat is a reactant. And that makes it really easy to predict what's going to happen to the equilibrium, because you all seem, and it's usually true, is that understanding what happens when we affect the concentration of a reactant or product is much easier to think about in terms of changing those concentrations, what happens to the equilibrium. So now if we just think of heat as a reactant, we should know what to expect. Okay, so the first example here, carbon monoxide combines with hydrogen to produce methane and water. Everything's in the gas phase. And we're given a delta H that is negative. Is that exothermic or endothermic? Okay, so this is exothermic. Whoop. Because of that, heat is a product. So I'm going to simply add it right in my equilibrium. So now, if we add heat by increasing the temperature, which way is the reaction going to shift to reach equilibrium? Or is the reactants or product? We're adding heat. It's going to go towards the reactant side. Okay. Everyone okay with that? Cool. We do the opposite. We remove heat. Somehow we decrease the temperature. Now we're essentially removing that product, the heat as a product, and we're going to force the reaction to go towards the product side. Okay. Our ammonia reaction is endothermic, so we're going to put heat as a reactant. Okay. And now if we add heat, we increase the temperature. The reaction is going to shift towards the product side. If we remove heat by decreasing the temperature, we're going to shift towards the reactants. Okay. Questions on that? Yeah.
Wait, so does adding or removing the heat, does that change the actual equilibrium value?
So does adding or removing heat change the actual equilibrium value? Yes. It does. So that is a mathematical question that is way beyond this course. So this is the key. This is what you need to know. When we are going to, in the next chapter, like I mentioned, look at changing temperature for a reaction, specifically looking at the autoionization of water. So water forming H plus OH minus, or H3O plus and OH minus. And looking at how the pH is changed by temperature. That is different K value. But this is, I can't combine them, that without using this difficult math. Yeah.
So when you add heat, does the moles of the gases not matter anymore?
Right, so if we're adding heat, moles of gas no longer play a role. Okay. We're strictly thinking about heat as a reactant or product. And then that goes back to changing concentration of reactant or product. And we really can't change concentration of heat, I understand that, but like that is a sort of tool that I like to use to have this sort of make sense in my head. Other questions? These are good. Yeah.
We have already taught in this course about multiple of these like things happening at the same time, so every time there's an air pressure change.
Yeah, we're not going to combine this. The question is, will we have to know what happens if you change both pressure and temperature? No, we're not going to combine those on you. That would be really difficult to predict. Yeah. Anything else? Okay. All right, so we're going to do this example. But it's actually, it looks like it's mathy, but we're going to skip the mathy bit, okay? So you can do the math on your own, but I want you to look at this example. So we've got a reaction of I2, iodine plus bromine forming 2 IBr, okay? There's an equilibrium value of 280 at 150 degrees C. If we put 0.5 moles of IBR in a 2-liter flask and allow it to reach equilibrium, what are the equilibrium concentrations? Okay. So this is sort of kind of a, we haven't seen a setup like this before. This is still an ice table. So I'm going to rewrite our equilibrium. Okay. We have initially no moles of reactants. Right? The only thing we have is a half mole of IBR in a 2-liter flask. So the concentration of IBR is, 0.5 divided by 2. So we're going to have 0.25 moles per liter. Initially in our class. Yep. So which way does the reaction proceed? So we only have product. This can proceed, and it's going to go towards the reactant side. Okay? So when we write our change line, we're going to have minus 2x of IBR. And the 2 is from the stoichiometric coefficient, plus x for BR2 and plus x for I2. So this might be, I mean, maybe you saw these in the homework, but this is one example where we start with only product in the container, so that you're subtracting product and adding in reactant to reach equilibrium. Okay. I just wanted you all to see an example of this. This is also, if we were to actually calculate equilibrium concentrations, another one of our perfect squares. Okay. So you can take the square root of both sides and then make that not a quadratic anymore to solve. Questions on it? I know that there's another problem in the homework. It's kind of a silly one, where we can use this same reaction. We have I2 plus BR2 in equilibrium with IBR. And you start with, let's say, 0.1 moles of I2. Does the reaction proceed? What do we form? Because we only have one reactant in this case, this reaction will not proceed. Okay. However, we can make it harder. Everyone's favorite thing to do. Have both reactant and product. Now we can make this reaction proceed. And we would have to solve for Q, maybe. Well, we're going to divide by 0. That'll be fun. But we would make this reaction proceed towards the reactant side. We're not going to work that one. But I just want you to see, this is sort of an application of the Chatelier principle, where if you don't have reactants, but you have all of the products, you're going to form reactants. Same as removing reactants. Okay? And that kind of thing. Okay, now let's actually do a problem. I'm going to let you all work on this one for a bit. We have at 100 degrees Celsius, the equilibrium constant for this reaction shown here has a value of 2.19 times 10 to the minus 10. And we're given a following concentrations of each of the reactants and products, and we want to determine if we're at equilibrium, and if not, which way does the reaction proceed? So take a few minutes, work that problem out, and then we will work on it together. All right, let's take a look together. So in our problem, we are given we are given concentrations, maybe not equilibrium concentrations. We're given concentrations of COCl2 of 2 times 10 to the minus 3, carbon monoxide 3.3 times 10 to the minus 6, and chlorine gas 6.62 times 10 to the minus 6. So we want to figure out if we're at equilibrium. So we're going to plug these values into our expression for Q. And then Q is just given by concentration of products over reactants raised to their stoichiometric coefficients. So what we'll put in here for carbon monoxide, 3.3 times 10 to the minus 6. Chlorine, 6.62 times 10 to the minus 6. And then COCl2, 2 times 10 to the minus 3. I got 1.09 times 10 to the minus 8. We agree? Cool. So then Q is what? Greater than K? K is 2.19 times 10 to the minus 10. And so which way do we head? Which way does the reaction proceed? Towards the reactants. Now, if you want to challenge yourself and solve a quadratic, you could plug all of these concentrations into an ice table and solve for equilibrium concentrations, making sure that you are adding reactants and subtracting out products. Next time we'll be starting chapter 16.